In the last week lecture session, we had discussed about half of Chapter 6. For today's lecture session, we will discuss about the other half of the chapter. Okay. Similar within the previous lecture session, there will be part of this lecture video where the students require to answer questions based for the lecture session's attendance. Okay, right, let us begin the lecture. As usual, I will start my slide by listing down sub-chapters of the Chapter 6. For this lecture session, there will be several sub-chapters to be covered. We will start our lecture with difference amplifier. We will discuss about operational amplifier application afterwards. Here, control source, instrument amplifier, and the active filter will be the sub-chapter which related to the three main chapter here. Okay, let us start our lecture. Difference amplifier. This type of op-amp is used to amplify the difference between two input signals. Here, as can be seen in this figure, clearly that this amplifier has two different input signals. Consider the op-amp circuit shown in this figure 5.24. Keep in mind that zero currents enter the op-amp terminals. Applying KCL to node A, each current component 1 and 2 will be the top equation in this slide. As we extend this equation, we can have the voltage output as the in bracket with voltage A and minus component with voltage 1. Later, by applying KCL at node B, we will have the function of VB using the V2. As been discussed last week, the relation VA is equal to VB. Then, we will have the VO as the top of the equation. After we extend it, later we will get the bottom equation. For understanding the difference amplifier in Chapter 6.6, we will take a look at an example here. Obtain the output current in the instrumentation amplifier circuit below. First thing first, we need to understand the figure which given to us. If we compare this figure with the one that we discussed before, it is almost the same. But, the arrangement of the V1 and V2 are the two things been rearranged. The meaning of the difference amplifier was the same. By applying the equation in the previous slide, we can have the output voltage is minus 0.04 volts. As we know the voltage at this point, apply the Ohm's law, we can find the output current from the output voltage here. Voltage over 50 ohm of resistor will get the current as minus 0.8 microampere. The example 2 here, require us to calculate the output voltage from the given resistor values and an input as 80 microvolts. From the given figure, we can divide the long given circuit here to be as 3 separated amplifiers using the red dot over here. Then, we have one non-inverting amplifier on the leftmost and the other remaining 2 inverting amplifier. As the 3 are connected to each other, we can write down an equation on A. A is equal to A1, A2 and A3. From here, as the non-inverting amplifier is concerned, we need to utilize the leftmost in bracket equation. The second and the third will be the inverting amplifier. As we insert all the value of the resistors, we will have the A is equal to 22.2 kilo. To find the output voltage, we can use the input voltage given in question multiply with the value of A here. Then we will have output voltage is equal to 1.78 volts. The example 3 is actually the same idea with the second example. Now, we can have two ways or two methods to solve this problem. Either we define A with A1, A2, and A3, or the other method is to find the intermediate VO for each amplifier left to right of the circuit given here. The answer is still the same, right? For this exercise, please take your time and do it at home, okay? As to summarize the amplifier, here is the types of amplifier which we had covered and discussed before. Begin with the inverting amplifier at top left, followed by non-inverting amplifier at bottom left. Later we discussed about the summing, which is at top right. Then, the voltage follower at middle bottom and the difference at the bottom right. As we can observe here, the inverting and non-inverting amplifier are related to each other, but different in terms of the additional of 1 with the resistor ratio. Now, let us go into the next chapter, which is op-amp applications. There are several sub-chapters in these chapter. First is control sources. Here, we have 4 types of control source. There is voltage controlled with voltage and current sources and current controlled with voltage and current sources. Voltage or current over here can be used to control an output voltage or current. An ideal form of a voltage source whose output VO is controlled by an input voltage V1. The output voltage is seen to be dependent on the input voltage, times a scale factor K. This type of circuit can be built using an op-amp as shown in this figure. 2 versions of the circuit are shown, one using the inverting input, the other the non-inverting input. For the connection of top figure, the output voltage is equal to -Rf by R1 to the V1. Whereas for the bottom figure, the relation is by the in-bracket component with the V1. For voltage-controlled current source, the output current is dependent on the input voltage. A practical circuit can be built, as in this figure, with the output current through load resistor RL controlled by the input voltage V1. The current through load resistor RL can be seen to be V1 by R1. The output voltage is dependent on the input current. A practical form of the circuit is built using an op-amp as shown in the figure. The output voltage is seen to be as VO equal to -I1 RL. In this type of circuit, an output current is provided dependent on the input current. A practical form of the circuit is shown in this figure. The input current I1 can be shown to result in the output current I0 so that 1 plus R1 by R2 in bracket with I1. Here is the example for the control sources. The question asked on how to calculate the IL. The IL is the current which flows at the RL. As voltage-controlled current source, I0 is V1 by R1. Therefore, 8 over 2 kiloohms will be 4 milliampere. Next, is the second example. Calculate the output voltage. As current-controlled voltage source, VO is minus I1 and RL. Here, we will have minus 20 volts. The second sub-chapter for the op-amp applications is instrument amplifier. A circuit providing an output based on the difference between two inputs, times a scale factor, is shown in this figure. A potentiometer is provided to permit adjusting the scale factor of the circuit. Whereas 3 op-amps are used, a single quad op-amp IC is all that is necessary, other than the resistor components. The output voltage can be shown to be is this equation below. Here is the example for this instrument amplifier. We need to calculate the output voltage. Based on the equation in the previous slide, we will have output voltage as 21 multiplied by V1 minus V2. To provide voltage amplification and signal isolation or buffering, active filter is been utilized here. Low-pass filter is generally providing a constant output from DC up to cutoff frequency, frequency O, and then passes no signal above that frequency. High-pass filter provides or passes signals above a cutoff frequency, frequency OL. While the band-pass filter will filter passes signals that above one cutoff frequency and below another cutoff frequency. Low-pass filter can be classified into two types. A first-order, low-pass filter using a single resistor and capacitor as in the left-hand side figure, and it has a practical slope of minus 20 dB per decade as shown in right-hand side figure. The voltage gain below as AV and the cutoff frequency is constant at 1 over 2 phi R1C1. The circuit voltage gain and the cutoff frequency are the same for the second-order circuit as for the first-order filter circuit, except that the filter response drops at a faster rate for a second-order filter circuit. This example requires us to calculate the cutoff frequency for first-order low-pass filter. As the given R1 and C1 value, the frequency can be calculated, and the FOH is 6.63 kHz. First and second-order high-pass active filters can be built as shown in figure on the left top and bottom. The amplifier gain is calculated using the same equation with low-pass filter. The amplifier cutoff frequency is FOL as 1 by 2 phi R1 and C1. For the second-order filter R1 equals R2, and C1 equals C2 results in the same cutoff frequency as in First order high-pass filter. The example for high-pass filter asked us to calculate the gain and frequency of the second order of high-pass filter. AV is equal to 6. And FOL is 1.5 kHz. The figure shows a bandpass filter using two stages, the first a high-pass filter and the second a low-pass filter, the combined operation being the desired bandpass response. Example for the bandpass filter. Calculate the cutoff frequency for these given values. For this FOL is 150.15 Hz and FOL is 7.96 kHz. With that, I end my lecture for this chapter 6 part 2. I hope that you all gained knowledge and ideas this chapter.
Okay, thank you guys for watching NMZH channel. Hopefully you can get knowledge and benefit from the videos. Thank you so much. Assalamualaikum.